Here's an example of solving an equation, and in this case we're going to use a property of one-to-one functions. The property is this: if f of x is a one-to-one function and we know that f of a is equal to f of b, then what must be true is a has to equal b for it to be a one-to-one function. So basically, to use this, we need to create the same function on both sides. Basically, the same bases, 3 to some, in this case 3 to some power, and over here we want to change this to also 3 to some power. Well, first we're going to change 9 into a base 3 expression, so it's going to be 3 squared, but we have to leave that to the power of 3 minus 2x. And on the other side, 1/27 is the same thing as 3 to the negative 3 power. If you think about it, 27 is 3 to the third, and then if we bring it up, it would be 3 to the negative third. And it's going to be raised to the x plus 1. Power to a power, we're going to multiply, so we get these bases kind of with one exponent. So we're going to get 3 raised to the 6 minus 4x. And on the other side, we're going to get 3 raised to the negative 3x minus 3. Now, since the bases are exactly the same, and the two expressions are equal, then what is in their powers must also be exactly the same. So this is not an algebraic thing where we're canceling the 3, we're just using this property to say if the functions are equal, then what's in their exponents must also be equal. So we discover that 6 minus 4x must be equal to negative 3x minus 3. And then all we have to do is solve. Add 3x, or I'm sorry, probably be better to go add 4x to both sides, you get x. Add 3 to both sides and you get 9. So we get x is equal to 9. Similarly, this would be the logarithmic form of a one-to-one property solving. To get it to this property, though, we have to have one logarithm on the left-hand side and a single logarithm on the right-hand side. So I need to combine these two logs, which is easy enough. It's they're added together, therefore what's on the inside gets multiplied together under a single logarithm. So this is going to turn into ln of x minus 1 times x plus 4. And this is going to equal ln of x. And then just, since we have an ln on both sides, then what's on the inside must be equal. So we're going to get x minus 1 times x plus 4 is equal to x. Now we're not dividing the ln's away from both sides, they're not just magically disappearing, it's just this property saying if the functions are equal to each other, then their insides must also be equal. So we're just dropping the ln's in a way. Alright, and then to solve this, we're just going to expand the left-hand side. And subtract x, since this is a quadratic, we want to get it equal to 0. We're going to get x squared plus 2x minus 4 is equal to 0. And to solve this equation, quadratic formula, completing the square. I think completing the square would be quicker. Unless there's factors of 4 that subtract up to 2. Don't think it's going to happen. So if we complete the square, it's a nice property or method to practice. You're going to take half of 2, which would be 1, positive 1, square it, and add it to both sides. And this is after I move the 4 to the other side, so we're going to get a plus 1 over here. So this side becomes the perfect square, x plus 1 all squared. This side becomes 5. So our final solution, after square rooting both sides and subtracting 1, is going to be x is equal to negative 1 plus or minus the square root of 5. Now the only thing we have to be careful about is this x right here. If we take ln of x, this number has to be positive. And we'll have to throw out one of these answers. It can't be negative 1 minus the square root of 5. That's guaranteed a negative answer. So the only solution is negative 1 plus the square root of 5.